All right. Thank you for the notification. I think sound should work now. Let's see. Works? No? Yes? OBS now says that there is sound, so I'm assuming things should be fine. Okay, cool. Yeah, Linux, man. There is this annoying problem in, trying to think. So like my memories of using Linux from 15 years ago when I last did this sort of religiously were that the main two failure points were audio and Wi-Fi. I'm pleased to report that Wi-Fi seems to work perfectly on Linux, at least in my setup. I have a Wi-Fi on board and I have a Wi-Fi card that is separate, and I think both work fine. Audio has been weird. The problem with the mic is if you start up the system, it doesn't recognize the mic, so you have to unplug the mic physically and then plug it back in, and then it recognizes it. And also when I updated on the newer Ubuntu version, I had to downgrade because of audio. Like everything worked except for audio. So I don't know what's up with that. Anyway, as I was saying, the goal for today, so technically we are going to be looking at optimizing the renderer, but it's not really. So what we tried last time was a bunch of, maybe the best word to use is tactical optimizations. Some of them helped, some of them didn't. We ended up not committing a bunch of them. Today we are gonna try to do a slightly more strategic one in hopes that it's gonna fix our performance issues with occlusion culling. Before doing that, that will require some restructuring of how we do things. That is gonna bifurcate a little bit, or maybe a lot, a rendering pipeline between when you use mesh shading versus when you don't. So it would be worth noting where we are right now. So we have this set up, we can render stuff, things are fine. By default, we enable all forms of culling except for cluster occlusion culling. The reason for that is that right now we are rendering at around 7 milliseconds per frame, give or take. At some point we'll need to look at some of these numbers because they're somewhat fishy, like some of them don't add up. Like we should be rendering at 6.5 or so, but for some reason the total GPU time is 7. Anyway, so when we enable cluster occlusion culling, the total render time increases substantially, but the number of triangles decreases substantially. So this is not a good place to be in. This means that we are introducing, or we are bumping into some overheads when we use cluster occlusion culling that negate all of the potential savings that sort of the occlusion culling gives us. This is unfortunate, and I suspect that if we succeed today, then hopefully we are going to recoup all of this overhead and more. So hopefully we're going to be in a much better place if what I'm thinking of works. But the first question to ask is what is going on? So brief sort of recap is going to be difficult to understand if you haven't watched previous streams, but the basic idea is this. We have two passes that we render things in. We are calling them early and late. So when occlusion culling, it's difficult because we have two forms of occlusion culling. Like it's difficult to talk about. We have two forms of occlusion culling. We have the object mesh-based one and the cluster-based one. So when we talk about only mesh-based occlusion culling, let's do it first. Then in the early pass, we render past visible objects. And in the late pass, we compensate for the fact that the past information is imperfect where, so in the late pass, we do actual occlusion culling. We render sort of false negatives, I guess. So objects that we thought aren't visible but are actually visible, and we update visibility status for the next frame. Under stable scene conditions, like all objects have the same visibility status, nothing moves, which is our case, after a couple frames it stabilizes, and so everything is rendered into early pass and nothing is rendered in late pass. Importantly, if an object is rendered in early pass, we do not render it in late pass. So these are exclusive. We can never render an object twice. When we implemented cluster culling, we unfortunately had to break this exclusivity for object rendering. Because when you render an object, half of the clusters are visible, half are invisible, but there's the same deal where you have to confirm the fact that the clusters are invisible. And when this attempt to confirm the past visibility status fails, you have to render them again. And so what happens for cluster culling is that in the early render, we render past visible objects and clusters. So only the clusters that were visible last frame out of objects that were visible last frame are going to be rendered in early pass. So this is a smaller subset than the total one. Like we are rendering, this is a substantial reduction. Like we are cutting number of triangles by half, so this is at least a 2x reduction. In the late pass, however, what has to happen is that we render past, or we try to render like the same thing like occlusion culling, etc., past invisible objects. This is fine because we haven't rendered them in the early pass, and this is called away really efficiently and stuff like this. Like this is not a problem. However, we also have to render past visible objects, but only past invisible clusters. And again, when I say render, I mean look at the cluster, see if it's visible now, even if it wasn't in the last frame. If it is now visible, then render it, update information, stuff like this. Again, under stable camera, you would expect to render nothing in the late pass and everything in the early pass. And this is actually consistent with what we get. We verified this last time. The problem is that we are spending a lot of time to render nothing in the second pass now. Let's look at the timings. This is a Vulkan stream. Yeah, I will not say any more than that. So let's look at the timings again. Under the default sort of case, the early, so we last time we split, if you look at the title bar, there is render and there is render late. And they oscillate a little bit because like the display shifts a little bit. At some point we'll fix all of this, but whatever. So when cluster occlusion culling is disabled, we spend 5.7 roughly milliseconds rendering things in the early pass, and then basically nothing rendering in the late pass. This is expected. This is a good case. This is what we want in a stable scene. When we enable cluster culling, we are now spending 4.36 milliseconds, so less, in the early pass. However, we also are spending 4.36 milliseconds in the late pass. You might be thinking, well, that's probably because we are submitting a lot of triangles. Like maybe there's a bug in the code, maybe we are rendering triangles twice. This is not true. This is not true. You can verify this by looking at the total triangle count, sort of. We verified this last time by looking at the per pass triangle count, like the number of triangles based on the hardware counter in the second pass that we render is 0. So we're spending 4.4 milliseconds rendering 0 triangles in the second pass. This is not a recipe for efficiency. Clearly something is going wrong. It is also suspicious that the early pass and the late pass it's the same time. Like the early pass does render triangles. It renders everything that you see on screen. The late pass renders nothing that you see on screen. It's difficult to just disable it. I talked about why in the last stream. So this suggests that we are hitting a bottleneck in actually both passes now that is unrelated to the number of triangles that we render, because in the late pass we render no triangles. This leads me to believe two things. One is, if we can fix this bottleneck, then the late pass should go to a number much closer to 0. Two, it is possible that the early pass is actually running faster than 4.36 milliseconds. It's just that we can't see it reach the smaller number because it renders because there is the second bottleneck, right? Because if you disable occlusion culling, you see 5.6 milliseconds in the first pass. If you enable it, you see 4.36. However, the number of triangles drops in half. So I wouldn't be terribly surprised if instead of 5.6, it actually should take us only 3 milliseconds now to render the first pass, but it's taking us 4.36. So we are wasting a lot of time on something that is bottlenecking the whole system. The other interesting clue is that we can disable level of detail. And when we do, it's hard to see a little bit, but the why is number of triangles dropped? That's kind of weird. Anyway, no, that is weird. But like when you disable level of detail, we render more triangles. It's just, I guess, maybe more occult in the end. Doesn't matter. What matters is the first frame, the first time increases because we are doing more work. We are not doing LOD selection, so we are always rendering the level of detail 0. Like that's a problem. The second time stays stable. So the second time seems completely independent of the number of triangles that we output. But also the other thing that happens when you disable level of detail is the total number of meshlets that go through the pipeline increases. I don't know, I don't remember if there's a hardware counter to look at number of meshlets. We are not using one if there is one. It does increase, like I just know, and it should increase substantially. So this suggests that not only is this bottleneck unrelated to the number of triangles that we output, because we output none and it takes 4.37 milliseconds, it also doesn't seem too dependent on the number of clusters that we render, which is odd because what else is taking time there is the question, right? So I have a theory, and the theory is this. So we are using distance-based, or maybe not distance-based. We are using some way to select level of detail based on the object's proximity to camera. So if you think about the pipeline that we have right now, the pipeline is actually the same between whenever we use meshlets and whenever we don't use meshlets. And it goes like this, or the high-level pipeline, right? So we have a bunch of objects. We have like 1 million objects. Then we have the shader, a compute shader that culls them, and then it fills the draw command buffer, where there's a single command for every object that we need to render. And this is where we do level of detail selection and object level culling and stuff like this. Again, I don't know off the top of my head. We looked at this last time because we looked at the counters. I don't remember what they were. We can do this again. I kind of don't want to. But there's some number of commands that is smaller than 1 million, but that is substantial. I'm trying to recall. 20K. It was in the tens of thousands, and I think it was in low tens of thousands, like it was below 100,000, I want to say. Let's just call it like 20K. It doesn't really matter what it is. So let's say we are generating 20K draw commands. And then every command draws a single mesh, which actually means it draws a number of meshlets. And then if we can look at the code. Where we fill these commands. So we are saying, okay, there's a meshlet that's visible. We are going to fill a bunch of stuff And whenever we fill data that relates to the meshlet rendering pipeline, we say, well, we are not using the traditional rasterization pipeline. So we're going to dispatch the task shader. And we are going to dispatch as many task shader sort of thread invocations as there are meshlets. So we're going to dispatch one thread per meshlet. And it's organized in groups, which is why we have to like divide and stuff like this. Doesn't really matter a whole lot. Then we tell the driver, hey, here's a bunch of draw commands. Each one dispatches some number of invocations of the task shader. Please like execute this. This is done using an indirect dispatch somewhere here. This is the command that does this. So there's a single command on the CPU that says, here's a bunch of commands. Each one dispatches a bunch of task shader waves, like do this. Every one command draws an entire mesh. So there's like tens of thousands of these guys. And then each command, we looked at this last time. I think the average number of threads that we needed was 60 something. I don't remember, like 62 or whatever per mesh. This is going to vary based on the triangle count, which affects meshlet count. So it's going to be different for different meshes in the scene. So this is just an average. So I think on average we are dispatching around one to two, maybe occasionally, groups of task shader invocations. Curiously, when you disable level of detail, like this number should go up, but our time in the second pass that draws no triangles doesn't go up. So what happens in the second pass after we dispatch all of this? We run the task shader with however many invocation counts. Oh, I have it open. The task shader does a bunch of work. Then it invariably concludes that in the second pass that we don't need to render anything because whatever we had to render was already rendered in the early pass. So it's an invariable conclusion. And then it outputs nothing. And all of this work takes a lot of time. It also takes suspiciously... Like, I haven't done the napkin math to validate this, but the amount of time seems unreasonable given the workload. Like, yes, we have a bunch of clusters that we need to cull. If we run with the 20K hypothesis, which I don't remember if it's true, and if we say that there is around 60 clusters, then there is about 1.2 million clusters total. And then for every cluster, we need to do a lookup into this depth pyramid and then do some like atomics and stuff. It's sort of a lot of work, like it's a lot of objects that we need to process and stuff, but it doesn't feel like this amount of work should correspond to the number of 4.36 milliseconds on this specific GPU. Again, this is something that ideally, you confirm using napkin math. The other thing I mentioned this last time, I looked a little bit into this and the conclusion is still the same. In an ideal circumstance, we would take this data, we would say, we are confused, we are hitting this bottleneck, let's try to pinpoint this bottleneck by using the graphics profiler. Unfortunately, so there is two graphics drivers that I have on the system, the official AMD driver and the unofficial one, RADV. We've been using the unofficial one for the last few streams, whenever we started using AMD. That supports mesh shaders. However, it doesn't fully support profiling when mesh shaders are enabled. I tried to hack it in today in the morning and my system crashed. So there's some work. It's a complicated mechanism. You need to understand how the GPU and the profiler works in order to make it work with the task shaders. I don't know how these things work, so I don't feel sort of qualified to do that. The other driver, AMD VLK, probably supports the profiler. However, it doesn't fully support mesh shaders. So they have some parts of the mesh shader pipeline implemented there. They aren't enabling it. The task shader implementation seems to be absent. So essentially, it doesn't work yet. Which means we don't really have the profiler, which means we kind of need to guess. So I have this guess. And we can validate this guess by doing more experiments, but I want to sort of try to get to a different way to render stuff, and then maybe that just works, and then maybe that is the experiment that proves the problem. And so the theory that I have is simply that the per draw overhead, especially in presence of task shaders and mesh shaders, is just too high. Because the logic goes like this: you disable level of detail that increases the number of meshlets that you render total. The amount of time doesn't really increase, and so it feels like we are hitting some. And you output zero triangles, so like you're increasing the amount of work, you output zero triangles. Something is weird. This means the bottleneck is on the stage that is higher level than the task shader, and the only stage like this is the draw commands. We are submitting a single indirect draw call. However, the hardware then takes this draw call and then executes one command at a time, right? This process may be partially serialized in certain cases, like there is parallelism in this process, but it is probably a smaller amount of parallelism than there is for, mesh shader invocations or pixel shader invocations or whatever. And also, when task shaders are involved, especially because AMD hardware doesn't natively support task shaders, so they have to jump through a few hoops to do that. Like, it might just be that we are hitting bottlenecks that are hard for us to fix. So this means dispatching too many draw calls may just be too slow here on the GPU side and in presence at least of task shaders. What do we do about this? Well, so one possibility is that the task shaders are the problem. You remove task shaders, you keep mesh shaders, and then maybe this fixes the bottleneck. However, if you remove task shaders, then there is no shader stage where we can call the clusters. So we have to call, and this is kind of what we are trying to do here. So we need to call the clusters in compute in a separate stage. It is possible to do this. We might end up doing this at some point, especially if the simpler thing doesn't work. However, this is not ideal. This is not ideal for a few reasons. One is on AMD hardware, there's no task shaders and stuff like this. Like the driver compiles task shader into a compute shader. It stores a bunch of data to memory or to ring buffer. Like it's emulated to some degree. But on some hardware, like Nvidia hardware, the support for all of this is more native. I don't know details about that, so I don't want to say it is natively supported, but it's definitely more natively supported, if that makes sense. So we might penalize some other vendors if we just say, oh yeah, task shaders are slow, don't use them. And it's not clear to me that the problem isn't like the task shader specifically doesn't look like, it looks like this connection between draw and task. So what I want to do then is I want to try to remove this draw count dependency from the pipeline while keeping the whole pipeline working. One thing that we should keep in mind is that we've been using a single mesh, but actually our renderer is capable of rendering a full scene. We just aren't like doing that. For example, let me try to oh right, I had some meshes in another. So I'm passing in two objects now, two paths to obj files, and the code that sets up the scene randomly selects which object to render. Curiously, in this case, by the way, oh no, never mind. Yeah, okay, cool. So we can't just say, for example, oh, instead of using many draw calls, individual draw calls, let's use instancing. Or we could say this, but I don't want to say this because then we lose this property that we don't actually care about the composition of each individual object that we render. Like we happen to render a lot of identical objects, but the code works just as well, hopefully, if we render any number of instances of any number of objects. And also level of detail selection becomes more complicated when you do instancing. So I want to keep the property that we use disjoint draw commands, sort of, but stop using draw commands, stop using draw calls. So then the thing I want to try is this. And I haven't looked up some of the limits on this, but let's just I guess maybe Vulkan info has these. Let me look. $4 million. $4 million feels reasonable. Okay. I don't know if 4 million is the minimum number mandated by the spec, but whatever. Let's try this. Let's see what happens. Maybe it works, maybe it doesn't. I don't know. I should mention, so this is all AMD hardware. Somebody benchmarked this code on Nvidia hardware. On Nvidia hardware, there's definitely less of a problem, as in on Nvidia hardware, at least enable cluster occlusion culling is a net benefit, not a net negative. I don't have access to the detailed numbers, so I can't comment further. And we haven't tried this on Intel hardware yet. We will. I have an Intel GPU. I tried to set it up like very quickly. It didn't quickly work, so I'll try to set it up at some point later. It should support mesh shaders. The drivers should have support for them. So I don't know how optimal all of this is, etc. But essentially, we don't have an evidence that what we are doing is fundamentally wrong. But there is some reason to believe that sort of not being bottlenecked by the number of draw calls is just a nice thing to have, nice property to have in general. So, what is the plan? Well, the plan is this. The plan is very simple, really. Instead of generating 20k or whatever it is draw commands, we are going to generate just one. We are going to just use one draw command. What, why is this good versus bad? Why is this interesting, etc. So, there's really one big thing that we get from using many draw commands. And the big thing is that we have these two independent indices. One is the index of the draw call, and the other one is the index of the meshlet that we get in our task shader. And so if you look at what happens in the task shader, we use this draw ID thing, which we use to index all sorts of draw commands that are generated. And this is how we extract the position of the mesh, etc. Like, we can't render anything without knowing which draw call we are rendering right now. The other thing that we get is we get the index of the meshlet, which comes in this built-in variable. And then we use that to index the meshlet data. And then the rendering proceeds. So we need these indices. Right. We need these indices. However, we need nothing else. As long as we can compute the meshlet and the draw call that we need to render in the task shader, I think we pass the... I thought we passed the task. Yeah, we passed the draw ID to the mesh shader because in the extension model, the draw call index isn't implicitly available in the mesh shader if you're using task shaders. So, but we kind of do nothing else. So what I'm trying to say is the model for task shaders and meshlets and mesh shader execution is such that the amount of implicit data that the API just gives you for free is very small. It's essentially nothing. We use the draw call index here, which is nice, but there's nothing else that comes with this for free. Everything that we do, we compute ourselves, which means that we are less dependent on there's more freedom to restructure the higher level of the pipeline when we use mesh shaders to say, oh, well, we are not even going to use the draw call. Like this thing is not going to be available because we're just going to use a single draw call. When we right now need to render two meshes. One has 3 meshlets, let's say, one has 5. The numbers aren't like all of this stuff is rounded to 64 and stuff like this. So like the small numbers don't make sense, but let's say this doesn't happen. What we do right now is we generate 2 commands. One says we need to dispatch 3 task shader threads. The other one says we need to dispatch 5. And then the API implicitly generates draw ID 0 and draw ID 1 for them. Cool. What we can also do is we can just say, well, let's just dispatch 8 task shader threads. And then somehow, when we are in the task shader, we will get a number from 0 to 7. If we can somehow convert this number to the draw call ID, right, saying, oh, the number is between 0 and 3, okay, this must be the first draw call. Oh, the number is larger than like 3 or larger, it's the second draw call. Once we get this information, everything else should work as designed. The benefit that we'll get, maybe, is that we're going to eliminate this whole sort of dependency problem that potentially exists somewhere in the driver or in the GPU or whatever. And maybe this will remove this bottleneck. However, changing this conversion, or like doing this conversion, is a little annoying. There's a few things that are a little annoying about this process, but the biggest one is converting. So like, let's say you have, because in reality you don't have just 2 numbers, you have like 20,000 of them, right? And how are you gonna select the correct index? Like you get a meshlet index that's like linearized in this way, right? So the meshlet index could be like 100,000. And the reason why you know it's a draw call number like 17,055 is because that draw call is the first one that references this sort of meshlet index. You can do that. However, doing this requires on the fly building some sort of data structures. I hesitate to call this data structures. You might need to like sort something, or you might need to do a prefix sum of some array on the GPU, and then you can binary search in that, and that will give you the index. This is what I would try normally, but I don't want to. The reason why I don't want to is I don't like computing prefix sums on the GPU. It is fiddly if you want to do it quickly. And also the idea of binary searching in every task shader invocation is a little weird. Like, I don't love this idea. Here's the idea that I like more. We are, in reality, splitting these invocations in groups of 64 anyway, because this is what determines the task shader workgroup size. So in reality, when we are rendering a mesh, we are not dispatching number of threads in the task shader, we're dispatching number of workgroups. So we say, hey, we need a workgroup with, we need a certain number of workgroups. And then if you multiply this number of workgroups by 64, you approximately get the number of meshlets that are actually going to get processed. And if you look in the code, in the shader code, then this is kind of what happens here. We take the meshlet count that we want to render, and then this macro is 64. So then you round it up by 64 divided by 64, you get the number of workgroups. What if instead for every workgroup, we were generating a command to sort of render it? The command essentially says this. We know the draw call that the meshlet comes, or that the number of meshlets comes from, or like we can get it from the draw ID. So essentially, what if here, instead of generating one command for every mesh, we were generating however many task shader invocations, task shader workgroup dispatches we were doing here, and for each one we would say draw ID. This would allow us to reference the thing that we need. It would give us the meshlet offset, which is the thing that we need to reference. It's an index into the global array. We needed to reference the meshlet data. And we need to specify meshlet count, which is going to be a value in 0 to 63 range. And we can maybe bit back these guys. So this is 6. We can like not bit back these guys. For this value, you realistically want more than 16 bits. For this value, you definitely need more than 16 bits. We currently only have 1 million draw calls, so technically we could do like 24 bits here, like some number of bits here, and 6 bits here. So maybe this is what we'll do. We'll do like 26 bits of draw ID, or we can. It's hard to know how to balance these bits, right? We could just use 12 bytes for the structure, but 8 bytes is better than 12 bytes. So I kind of want to keep things to 8 bytes. So maybe we'll bit back something. Maybe we'll bit back just offset and count for now, because offset realistically is not that big, unless... In our case, anything works. I think in the production renderer, I'm not sure what I would do in the production renderer. You can distribute bits somehow. You can like pack 2 bits here and 4 bits here, vice versa, whatever. So we'll do some bit packing scheme that happens to work for us here. So we'll generate a list of these commands. And then we'll just dispatch a single invocation of the task mesh shader draw call. And then we'll have to read the draw call from this buffer, etc. This is not going to work at all for the, or it's not going to work too well, let's put it like this, for the regular rendering pipeline. Although now that I think about this, you can sort of make it to work, because you can slice things into the index count buckets. But it's not clear why. The reason why, oh, right, yeah, sorry, you can, right. So in a traditional rendering pipeline, the reason why we did this in this first place, this way in the first place, is not just for convenience, but also because when you're not using mesh shaders, you kind of need the hardware to read the index data. And for this, you have to use the offset and count for the index, which we specify here and here. And you can't just merge multiple disjoint sort of indices in different places into a single draw call. Like, that doesn't work. But for us, because after a draw call comes a task shader, it can decode arbitrary data however it wants to, we have this flexibility of saying we don't need draw calls. We can just generate something else. So the downside is, instead of having roughly uniform pipeline that splits briefly into this bifurcated traditional versus mesh shading, we are going to have to write some code that only ever executes under mesh shading pipeline, even though it kind of runs here. But this is fine. This probably is not that complicated, and if we need to do it for performance, then we need to do it for performance. So that's the plan. Let's try to do this. Let's see what happens. Maybe this improves performance, maybe not. The other thing I will mention, I mention this every time now. Linux does not have a good strategy of recovering from GPU crashes. We're going to try to be very careful and not induce a GPU crash. It is not very difficult to induce a GPU crash when you work with this stuff. Vulkan by default doesn't have... we can enable this, but there's like basically some out-of-bounds read and write protections that Vulkan by default just doesn't do. And I don't want to enable it because I don't know if it works well with mesh shaders. Like, I don't want to, it's an extra variable that I don't want to like introduce right now. So we are going to try to be careful is all I'm going to say. And then, oh, there's the visibility offset also. Oh, we need more stuff. Okay, we'll figure out the backend thing. But yeah, so we are going to try to be careful and not crash the GPU. Hopefully we will succeed, but you know, if you crash the GPU, then we'll have to, essentially what happens if the GPU crashes is the stream goes down, I have to reboot the computer, and then I can resume the stream, but there's going to be a blip in the stream of like a few minutes. So if you see the stream just like freeze, then it should hopefully come back in a few minutes. We haven't had this happen, but I keep anticipating that this would happen, and so I keep warning about this. All right. So the preamble is done. That's... yeah, so thankfully the reboot is quick. Now I have to like bring up programs that we're running and stuff like this. So I don't know how. We'll try to make sure this doesn't actually happen, but it's hard. It's hard to be 100% sure. All right, so. So the first thing that I want to do is I want to actually figure out, let me remove the tablets. So we have this method command right now. There are some benefits of separating things like this. Right now we actually sort of merge the raster and mesh shading path, and because of this we sort of use more memory for measure commands than we need to. So splitting things into more like isolated, this is just for traditional, this is just for mesh shading, is nicer in certain ways. But it's not always ideal. So the first thing that we need to do essentially is figure out how we make a buffer, figure out sort of how we're gonna structure this. I'm not sure what to, let's call this mesh task command. It seems reasonably indicative of what we are doing. So what data do we need? So we need the draw ID. Then we need the offsets. I'm gonna call these task offset task count. And then there's this stuff that we probably also need. So this is just a single, we were just not caring about memory at all. We might need to care about memory. Right, so I forgot to mention, the downside is there's more of these guys than there is these guys. So you're using more memory for command data, right? How much more? Depends. There's a variant of the thing that I'm gonna try to do right now where we say, oh, we're just gonna generate the list of meshlet indices. So it's essentially this thing. And then just generate one giant array and then not even use task shaders, like use that thing. This doesn't play super nice with culling, so I don't want to do it, but also it needs just more memory, because so there's some number of triangles that you need to render. There's approximately that number divided by 64 meshlets that you need to render, but the thing that we are going to try to do here is that the number of meshlets divided by 64 again. So it's number of triangles divided by 4,000. So it's not that many commands, but it's still probably more commands than the raw commands. Anyway, all right. So we need these two guys. So this is an array. This is an index. This we might remove and rework in the future. We need this for now. This is like an offset into a visibility thing. And this is 1 bit. And we need this because somewhere in like, right, in the task shader, we use this to, there's complex Boolean logic. I don't want to go into this again. Okay, so we need 5 things. We need 5 things. So this is like, let's say 24-ish bits. This, it's hard to know. Let's also say it's 24 bits. This is 6 bits. Let's just say 6. This is 1 bit. This is pretty big actually, because it's a linear index into this giant array. We have reduced the number of bytes in this array, but we haven't reduced the number of bits in this array. And I think this is a bit offset. And so this is like a lot. It was 1.2 gigabytes, so it must have been 400 million of bits. So this value must need, what is it, 26 bits at least. So let's just say 32. We will probably rework this guy in the future, but this is kind of what it is. So if you eyeball this struct, then you kind of can see that as it is right now, it doesn't really fit into 8 bytes. There's just too many bits. Like these 3 things alone add up to like over 8 bytes. So let's just try to pack this into 16 bytes for now. 16 is a nice number. It's a power of 2. It's large-ish, but not like it's not obscenely big. To simplify bit packing for now, I'm gonna say that here we are gonna pack two values, low 31 bits. It doesn't really matter. Let's just say low bits, higher bits. Meshlet visibility offset. So for now, let's just do this, and then we will keep these guys unpacked. I had an idea of how to rework this thing, but this idea can only be validated once we resolve the performance issues like everywhere else in the stack, which is what we are doing right now. And if this idea pans out, then we might not need this offset at all. And if that is true, then we might be able to pack this whole thing into 8 bytes. But for now, let's just keep it to 16 bytes. So this is going to be the array that we are filling instead of this array. For now, we're going to keep this thing because we will try to preserve the old path, like the old mesh shading path. Like, I don't know if this will work out, right? So I don't want to rewrite everything yet to use this technique. So let's see. I don't know if we even need a CPU side definition of this thing. We do need this guy because we do need this guy. I don't know if we need this guy on the CPU. We probably don't even need it. Well, let's just keep it and on the see. At some point, we need to make an effort to share all of the structures between GLSL and C++. It requires a little bit of code massaging, which I have been avoiding. At some point, we'll do this. Okay, so then whenever we run this compute shader, we fill this buffer and stuff. We fill this buffer with commands. We won't need this buffer at all because this buffer is going to be replaced by this new buffer. So I'm gonna use this. There's this interesting technique in GLSL where you can alias two buffers onto the same binding, and this gives you a way to sort of write to the same destination pointer, but fill different types in that destination. I'm gonna do that because we could just write a new shader. However, we are gonna wanna reuse all of the culling logic and just change this bit. And so it's gonna be easier for us, I think, to keep it in one shader for now. And this means we can also reuse, we are gonna be reusing the same buffer that we are filling right now. It's called DCB for draw command buffer. Right now it's 128 megabytes. There is this question, is it enough data? Which boils into how many structures do we generate. So we just said it's 16 bytes. So 128 megabytes gives us a, what is it, 8 million sort of entries in that buffer. Is it enough for what we need to do right now? Well, it's hard to know, but every entry in this buffer is gonna render around 64 clusters, which is gonna render around 64 triangles. So this is 4K. So this in total is 32 billion. So we don't have 32 billion triangles to render. So this is probably okay. The reason why I'm mentioning this is ideally, we are playing fast and loose in certain places of the code with like sizes of things in terms of limits. Ideally, there would be a limit that says, hey, you can render up to, 32 billion triangles or whatever per frame. And whenever we write to the buffer, we are going to check if the write goes out of bounds. We are not doing this right now anywhere. But ideally, this is what you should do. I might just leave a comment about this somewhere. All right. So, let's add a second specialization constant that says, I don't know how to call this new path. Let's just put task here. It's a little bit awkward because it's not. Let's just put this here for now. So when we are in this mode, I essentially want to do the moral equivalent of whatever we have been doing so far, but with this new mode, right? So we have some number of meshlets that we need to render, and we need to, hold on, sorry, this index needs to go here. So we have some number of meshlets that we need to render, and we need to fill commands that are associated with this meshlet data. Instead of just filling one command as we do here, we need to fill more than one. How much more? Well, it depends on, it's the same number that we were dispatching here. So this is the number that we need. Then we need to allocate, using the atomic increment, enough sort of memory in our buffer for the commands, and then we need to fill all of them. So we are just gonna like fill them without any remorse. So this is this thing that we need to fill, right? So it's going to be DCI plus I. Okay, so the draw ID is always the same between all commands. And then there is task offset, task count, and meshlet visibility data. Okay. So the task offset here is always the same. It's this is the offset in like an array of meshlet data that actually can be used to sort of look up all of the meshlet information. So the first command that we need to render has the same offset. Essentially, basically we have, let's say the number of meshlets that we need to render is like 75. This splits into two groups. One is the group of 64 and the other is the group of 11, which is the remainder. And here we simply need to sort of keep offsetting this by whatever like the current group is. So similarly, in the all groups that we are dispatching except for the last one have the task count which is full, so like this one. So if I is task groups -1, then it's the remainder, and the remainder is LOD meshlet count. Is it simply modular? It's not simply modular because this can end up as 0. Hold on, this math is a little different. Oh, actually, there's an easier way to do this. So we can say, right, the easier way to compute this goes like this. We can say, okay, so the total number of tasks that we have remaining to render is simply this. And then for the last group, this value is correct because this is the remainder. For all of the previous groups, this value is going to be large, like it's going to be larger than what we need to do, or what we need to like dispatch. So I think this is the correct computation. In the first group, it's gonna say this value is large. So yeah, okay, I think this is correct. And then meshlet visibility data is this bit offset. Oh, no, sorry, hold on. So the we are bit packing the thing. Okay, so let's bit back here. So we said that we are going to be multiplying this by 1 and ORing the draw visibility, which is just 0, 1. And then again, for all, this value has to be like offset by the thing, but the offset needs to be shifted by 1 because of bit backing. Due to bit backing. All right, so this seems to be roughly what we need to do. Notice that this code only runs in the special mode that we aren't using yet. I should add, let's compile this variant of the shader wherever we are doing that. We'll have to have like 2 more pipelines. Hold on. Draw call task and draw call task. Should we just, we can call it task call or something like this, it doesn't matter. Okay, so we are compiling these 2 variants. Let's look at when, okay, perfect. So we need to destroy this, which we are gonna do. But okay, cool. So then we can just dispatch this stuff. Okay, I think we are, let's destroy this so that we don't forget. I think it's safe. So right now, if I try to run it, we are going to compile the shader code that we've written, but nothing will change because we aren't going to use these new variants yet. So I think it's safe to compile and run right now. So we are being told that, oops. Oh, right. Sorry, it's not draw commands, it's task commands. We were lucky that if this field didn't exist, something would have gone very wrong if you try to, like, it's good that there was a field with a unique name. Okay. So I don't know if these calculations are correct. It's going to be difficult. If something goes wrong, it's going to be difficult to debug this, even if the GPU doesn't crash, because like it all runs on the GPU. We can debug this if need be. It's just not going to be particularly fun. So it would be nice if this code was just correct. Offset one, shift by 1. Yeah. Okay. I think this is correct. This looks reasonable. So, this looks reasonable. Okay. Now what we need to do is that in a special mode that we don't have yet, which is, I don't know how we call it, task submit enabled or something, which we're going to disable by default. There's a few things that need to happen. So the first thing that needs to happen is simply that whenever we run the shader, we need to run the task submission can only work if you use mesh shaders. So where's the loop? Let's add somewhere here, let's say okay, and let's try to never use this variable without let's try to never use this variable. Is this okay? Yeah, I think this should be fine. I think this should be fine. Okay. So when we use this new mode, we're going to run this new variant of the shader that is going to fill different data. After this, what's going to happen is that when we render, we can't keep doing what we were doing, because right now we are saying, oh, here we are saying, well, we know we have ran this culling shader that has filled mesh draw commands and has filled a buffer with a counter with the number of commands to execute. So let's just like use that to execute stuff. This cannot work. So, or rather, if task submit is set, this cannot work. Otherwise, this is fine. I'm tempted to run this in this way because here's what should happen. Oh, right, I have to change. Actually, yeah, I don't. Okay, I want to try to run this in this way because what is happening right now is that we are going to run the new compute shader. It's going to fill a bunch of stuff, and then we are never going to use that and never going to use mesh shaders or task shaders. So I think this should work in as much as it renders nothing but fills some data, right? As in nothing should go catastrophically wrong, and it's going to give us a checkpoint where we said, okay, at least the compute shader didn't like blow up or whatever. So that seems reasonable. I'm a little scared because again, any run at this point may crash, and it's not going to be fun. Okay. You know, you only live once, so let me look at chat. Yeah, so Min is correct there. I always mix them up in these cases. It's like there's this weird mental thing which is like you want to compute the minimum, but it's you want to compute the minimum to limit the maximum of the value, if that makes sense. And I always mix them up, but I think Min is correct. Yes, it is the same PC. And yes, we have no proper profiling tools. As in, our profiling tools don't work with the technology that we are exploring. At some point, okay. All right, so I'm going to try to run it. Let's see. So if I press T, then what should happen is we enable this new mode. Let's actually look at this. This enables this Boolean. This means we submit no work at all. And this means we use the new shaders, which we have created. And these shaders are, I'm just like triple checking stuff. Okay, I think this is correct. Who knows? Let's press T. All right, nothing exploded. Good. There's one other thing that is worth noting, which I expected would happen, but let's talk through this. So when we press T, or actually we can't conclude this, right? Sorry, never mind. We can conclude much. I was gonna say you can look at timings for culling that got a little worse. From 0.03 to 0.1. I actually expected this because there is like more work that we are doing now. We are filling more data probably with draw commands, etc. Like it's legitimate to expect that we are moving some work, which is this draw call distribution, into task groups from the late rasterization stage into this compute shader. But the increase seems to be minimal. That said, when we do this, a bunch of stuff doesn't work right, in the sense that like who knows what's happening right now. It's filling some commands with something. God knows, anyway, nothing crashed. We will take the win. Okay, so what else? What next? What's next is we generated a bunch of commands. We have to use them. Well, the first thing to do that has to happen is that instead of this guy, which says here's a bunch of commands to render. Read the number of commands from a buffer and then execute them. Now it's different. Now we don't have the number of commands in the buffer. We just have a count of task shader work groups that we want to dispatch. There should be a different one, a different function for this, which we are gonna fish out from the spec in a moment. This guy. So this is saying that yeah. Oh. Cool. This sounds good. So, we only have a single toggle, so we now need to use this command. And when we pass this command, we need to pass it a buffer with data about the dispatch. What is that data? Well, unlike previously when we were when we had a buffer with just a single value, which is number of draw commands, and everything else was in that array, now this buffer has you can dispatch more than one draw call, but we essentially are merging everything into a single draw call, right? So this buffer has an array, but since we have a draw call count of 1, it's only one value of these structures. If you look at what we were doing previously, we were dispatching these one-dimensional task groups, which is the plan still. But we need a buffer. We have a buffer now with the count of things we want to dispatch. Instead, we need a buffer that has 3 values, not 1, and the last 2 need to be 1. I don't want to make a whole new buffer for this. It feels wasteful. So let's just add 2 ones to the buffer that we're already filling, I guess, and just be done with it. I don't know when exactly we should we fill, should we like fill it with ones and stuff? Yeah, sure. It's a little bit cheeky, but like I do want to mention it's a little annoying. So this 3-dimensional thing for task shaders kind of makes no sense. My understanding is it just complicates the spec in this particular area. I think they did it for consistency. So Nvidia extension doesn't have this. Nvidia extension has a 1-dimensional thing. Everywhere else in the API, we pretend that there's like this 3D grid of stuff that you dispatch. In some cases, a driver can do interesting things with the order. Unfortunately, on AMD hardware, at least, I think even the order of these things is not even interesting. It's just linear. But in task shaders and mesh shaders specifically, it's hard to know. This is coming from the days when people said, you have a compute shader that you are going to use to process a 3D texture. How are you going to do it efficiently? Well, just say what the tile size in 3D of your processing unit is and let the driver figure out what the optimal order and stuff is. But it kind of feels like sort of a vestige of the past, which is why I don't want to spend a lot of mental effort to figure out, oh, how do I efficiently fill a 12-byte array, because these 2 numbers are just like bogus. Like I'm not interested in these 2 numbers. All right, so yeah, we are just gonna use this guy to like fill this buffer. So this thing says at offset 0, write 4 bytes, and every 4 bytes that you write, take from this guy, which is 0. And so this should say start at 4-byte offset and then fill 8 bytes. Every 4 bytes that you fill them with the 32-bit integer, which is 1. So this fills group count y and z for task submit, and then fills group count x for task submit, or draw basically indirect draw count for regular submit. Okay, so that is good. Now this buffer in theory is in a good state, like it has the right data in it. So in theory, we can just, where is this guy? In theory, we can just call this thing, pass it command buffer, pass it the counter buffer. Things are lining up super nicely. For example, previously we already passed the buffer with the actual commands to the shader because we needed it to extract some extra info. So we don't even need to change any of this code, I don't think. All right, so buffer and then offset 0, and then we only have a single draw call, and then stride is the byte stride, and then if it's less than or equal to 1, it's ignored, so we can just pass in 0. So in theory, this is the code that we need to run. Now, if I run this right now, something breaks probably. The reason why something probably breaks is that we are still using this original array of commands that we were writing and the ID of the draw call, whereas we should not be doing that. In order for us to not be doing that, we need to specialize this shader for this new mode, right? Let's check the mesh shader first. So again, right now we are still maintaining 2 pipelines for using mesh shaders, task shaders. If the new pipeline works out, we wouldn't need to do this, but I don't want to commit to that yet. I'd rather it worked, it's fast, we commit it, and then we clean up as a separate step. Let's look at the mesh shader. Okay, so let's delete this for sanity's sake, so that we know we're not using it. And then we can't use draw ID. So I think the mesh shader is fine as it is. The task shader already has to do the heavy lifting essentially of dispatching the mesh shader waves and giving them the draw ID and telling them when the data starts and all of this. So in theory, nothing has to change here. Things have to change here. So just in the same way, we are going to add the task boolean. And then on the CPU, we need, again, variants of stuff. This is getting gross a little bit, but this one we can remove if things work out, right? So I don't want to pay too much attention to that yet. From this perspective, it's possible that right now we're going to make a mistake that we would have been able to avoid if we didn't try to maintain both things, but I kind of want to maintain both things. It's convenient to be able to toggle at runtime between 2 behaviors while you're optimizing them. Even if it makes the code a little bit more complex. Okay, so the name is kind of stupid, but let's call it task pipeline to go on with the previous naming scheme. Okay. Oh, this is a dot. This should be a comma. Okay. So this is true, this is true, this is task. Okay, now let's look at where we use these guys. Okay, it's nice and sweet. So we will destroy them here. Again, the names are a little bit misleading, but okay, so now we are using the pipeline built in this new mode, but we are not using the fact that, so we need to do 2 things. One is we need to stop using this guy. which we use in a bunch of places. And then the other thing we need to do is we need to stop using GL_ID. So first, let's move all of the references to this stuff to the top of the shader. So I want to move them all like here, basically. So first, task count is needed here and here. Okay, so we aren't using draw commands anymore. We're still using draw ID. We are not. Okay, cool. So now this block of code needs to change conditionally. Oof. Okay, that is fine. Oh, where is the offset? Wait, how come we are not using the visibility offset? That makes no sense. Hold on. Whoa, whoa, whoa. What? How did that happen? What the heck? What? That makes no sense. These offsets are gonna be, okay, so this is the difficult part. We have a bunch of places where we read a bunch of data that are all indexed in different ways, and we need to get all of this right. So this guy is gonna be a problem. Or we'll have to be very careful with all of these indices because they're used in interesting ways. Okay, so meshlet visibility offset here is red. Right. Why did we need it in the command then? This is interesting. Why do we need it in the command? Oh, is this a leftover from... Yeah, you know what? I think this is a leftover from... Yeah, when we were debugging stuff last time, we were... Is it? This is weird. Why the heck do we need this? So this guy we do need because we need to toggle like a thing. But this guy we don't actually need. Is it a good idea to remove it right now? Yeah, probably. So I want to try to remove it right now because I don't know why it's there in the first place. Maybe it was accidentally, like I bet it was accidentally sort of there. Okay, so if I run the code right now, it's going to be unsafe to switch to the new mode, which we're not going to do. But it should be safe to run the code. So on run the code, remove the variable, confirm that things work, run the code again. Let's try. Okay. Test occlusion color. Okay, so I don't think this guy is necessary. This is some weird, maybe this is a debugging sort of leftover, maybe not, who knows. The reason why it's useful to remove this is that then here we can stop doing this bit packing and we can even pack stuff in the future into 8 bits, more or less. Yeah, so I kind of wanna, and I said we are gonna remove this. Let's remove this from this. right now, because I think it should, like, if you're not using it, let's not touch this guy yet. Hold on, let's be careful here. Remove it from here. So remove it from here. So this doesn't actually appear to be used. So now I think I can compile and test. Yeah. I'm like enabling occlusion culling and disabling it and stuff and scene. Okay. So we didn't actually need this guy. Okay, so this is good because this means that we can just... Now this thing is easy to pack into 8 bytes, which we are not going to attempt yet because this will complicate our code, but we are going to do this once things work. Let's just, I guess, read it here. Maybe the compiler will move this guy, maybe not. Oh, are we calling it late draw visibility? Okay. Oh, this is not the... Okay. Okay. So, let's keep going. Sorry, this was a diversion. All right. So when the new mode is active, there's a few things that change. So one is we just need to read stuff from different places in the different array. This needs to be done like super carefully, because if you mess it up, things will not work very well. This global invocation ID is weird. So this is going to be the hardest thing. All right, let's do the easy stuff first. So just the same way as we did there, we're going to ls the buffer. We are gonna say that we have 2 arrays. We're gonna be careful to only use the right one. So when we are using this task shader mode, so if we just run things right now as they are, the issue is gonna be twofold. One is we aren't even filling this guy, so every read from this guy is extremely unsafe. 2, this value is always 0, and so even if we don't read anything from this guy, you know, we aren't going to render like multiple draw calls in a reasonable way. So what inputs, what are the inputs to this task shader thing? So we have added essentially all of the task shader workgroups. I will need to keep referring to documentation because it's all... There's this IDs and indices and stuff, and like, okay, let's see. For every command, we are dispatching one work group. Because of this, this is the command ID. And all reads, if things work out once, basically right now the code is going to be a little messy, we can clean it up, but I want to get it to work. Okay, so this is how you read the command data. For every workgroup, there is an element in the array that has draw ID and a bunch of stuff. This is how you do that. So that is easy. Everything that is stashed in the same place is also easy. So here, for example, we say, okay, oh, it's task, read it from task commands, indexed by this guy, late draw visibility, otherwise read it from draw commands. Same thing here. Task commands GL workgroup ID X, task count, otherwise here. Okay. These two I will need to think about a little bit, because oh, I don't. No, this is all super simple. Okay, I think we are good. So before, when we were running the task shader, we were running the task shader for the entire mesh at once. Now we are running every work group individually, but every work group processes 64 meshlets, up to 64. And this guy, G, stands for group. And previously we were computing it like in this global fashion. But actually what we need is this. So this is going to be under the new mode. This is going to be value from 0 to 63 because this is how the sort of compute shader-based execution model works. All right, and here we simply need to do the same thing. Work group. Task offset. So I think this actually works. The only thing that doesn't work is this guy. Oh, this is what I get for, we actually do need this. Oh, shit. Okay, fine. We didn't need it in the old pipeline. This is why I added this. I thought we would need it, and then we actually didn't need it, but we do need it in the new pipeline. Yeah. Ugh. If this code is correct otherwise, then it would be safe to run, but this value will not be correct. This is annoying. Yeah, okay. All right. You know what? Forget bitpacking for a second. Let me just add this guy. So I need meshlet visibility offset. Or I can just, I guess, move this guy here. Yeah. This is annoying. Okay, fine. So then we do need this guy. All right, let's just have it 20 bytes for now. I don't want to redo the bit packing that was undone. Did I add it after? Oops. Yeah. Okay. Yeah, I think this is correct. There is like probably a better way to organize this, but maybe not. Yeah, it wasn't. I was too hasty. Draws DI. Okay. I kind of low-key hate this offset value, but I was saying like there's a way to remove it. I just don't wanna. It's a little okay. So things compile, and in theory we have done whatever we needed to do. Is it safe to try actually running the new code? I have no idea. Let's try to validate. That things are okay. The first thing I should mention is these two values are only used when cluster culling is enabled. Sorta. They might be used and just don't matter when it's disabled. But we are not going to try that first, so this is probably safe-ish. But let's try to audit all of this again. So task offset says it's poorly named, but it basically says where in the giant array of meshlet data do you start reading meshlet data. And that seems correct. Correct. Task count says how much to read. That also seems correct. So then this guy is the same, and it's just a bit. And this guy says where in another giant array that is indexed a little differently from the first giant array do you read the bits corresponding to the individual meshlet visibility status from the last frame. Which I think is correct. So then we look at this guy. Let's make sure that we never use these when task is true. That seems correct. This guy is less dangerous because the worst case is it's going to be 0 and nothing will crash. But okay, we are not reading this. So we're using workgroup ID to index commands. This is because we dispatch one workgroup for every command. This is going to be a value that's usually 64, but sometimes smaller. This is going to be a value that's between 0 and 63. This, I think things are correct. I can spot any obvious bugs. What this means is we should try running this code and maybe things explode, but if they don't explode, they either work or don't work, and then we can think about what happens. I think I've done all I can ahead of time here to prevent any like obvious blowups. Let me double check what happens here. This is suspect. Why? Oh yes, okay, that's correct. I think things are correct. Let's try to run it and see what happens. This is Ubuntu. Let's try to run this and see what happens, and then maybe things blow up. So I'm gonna press T, which is gonna activate the new mode. Oh, sorry, hold on. Let me first double check that I'm running with validation. Yeah. There were some performance issues with okay. Let me double, like, I don't want to end up in a situation where we have a mistake that was preventable through through use of validation. Okay, so the previous implementation of mesh shading seems to work. The non-mesh shading implementation seems to work. Everything seems to work. I'm gonna press T. It's gonna activate the new mode. We'll see what happens. Worst case, the stream goes down. We'll restart it in a couple minutes. I pressed T and nothing happened. Is that a good thing or a bad thing? I think this means things aren't obviously broken. Let's. I don't trust. I don't know what I don't trust. Did T? I guess we know that T did something because we tested it when the rendering was just being. Okay, so maybe things work. So let's press T first. It's gonna activate the new mode. Timings did not change at all. Which isn't, well, yeah, timings don't change at all, which is interesting because I really need this mode to be like, oh great, okay, hold on. Like, so the one problem that we keep running into is there's just not enough space in the title bar to print, to like see stuff. Okay, so when I switch between the mode, I don't see any changes in any timings. Well, there's like a little bit of a change in the render time. It actually might be getting a little bit lower or a little bit higher, like whatever. There's like a very, very small change. By itself, this is not necessarily surprising because without occlusion culling, we haven't seen an evidence of adverse effects of all of this drawable stuff. The real test is in the new mode, how does cluster culling work? Let's try. Yeah, that's what I'm talking about. So, it might be difficult for you to see, but here's what I see roughly on screen. The total time is 4 milliseconds or 4.5 or whatever, like way lower than whatever it used to be. The render time for the first phase is around 2 milliseconds, way lower than it flickers like crazy. I need to, we'll deal with this. Let's say it's between 2 and 3. This is way better than what we had before starting to do this, because remember we had 5 without occlusion culling and 4.3 or something with occlusion culling in the first pass, and then also 4.3 in the second pass. Now the first pass dropped from 5 not to 4.3 but like to 2 to 3, so it is dropped more than 2x actually. More than 2x is not surprising. Why is it not surprising? We have half as many triangles. Why can it take less than half as much time to render? Well, the thing I haven't really talked about too much after we did the occlusion culling for clusters, because there was other stuff to do, but on the last 3 streams or so, I keep talking about the single most important thing in all of this. It may be very valuable for you to do an optimization on a higher level, because even though you can do similar optimizations on the lower level, the cost of doing that may be more than doing that at the higher level. So you have to always balance how much work do you save from all subsequent stages. Here, the number of triangles doesn't change based on, how do I put this? There's two things that, there's multiple things that are fighting each other. It is faster to reject clusters than it is to reject triangles. So when you reject clusters, you reject the number of triangles, like reduce number of triangles that is getting rendered on screen. But also you remove work from the stages below the cluster culling, which is mesh shader, that are doing per triangle culling work, which we did a few streams ago. And the rate of that reduction is larger, potentially, than the total rate of triangle reduction. For example, essentially, maybe you have, maybe when you have culling enabled, the triangle count drops from 10 to 5. But when you disable some stages of culling that are currently enabled, maybe the same optimization, instead of dropping from 10 to 5, it would drop from like 100 to 10 or something like this, right? You can't, it's not obvious what the actual sort of reduction rate is for any higher level optimization, because sometimes there are lower level optimizations that kind of backfill the need for that, but doing that can still be beneficial because it reduces the total amount of work that has to happen. Anyway, so this seems like a giant success to me, because we have implemented the thing. The thing seems to work. I don't know how to like test it, but like all of the buttons that I'm pressing seem to work. It is way faster. It is the same performance when occlusion culling is disabled, which essentially means that until we implemented cluster occlusion culling, we were drawing enough triangles and saturating the mesh shader stage of the pipeline enough that inefficiencies in earlier stages weren't really apparent or obvious. Now, when we do as much culling as possible, as early as possible, the efficiency of early stages is very critical. And especially given the fact that, as I was saying, we render the objects, we submit some objects to the pipeline twice. In fact, a lot of them. And so this maximizes, this makes it critical that the early stages are as efficient as possible, which this new implementation gives us. So now we can commit this code and then clean things up, because it's obvious, it's very obvious now that we just don't need the old mode. The new mode is so much faster with mesh shading enabled. We still need the old mode for a traditional rasterization pipeline. But when mesh shaders are used, we just can switch to this thing wholesale. The last thing I want to mention is, I was saying at the very, very beginning of the stream, right, that I am suspicious, like the amount of work that needs to happen to call the triangles, the clusters in the second phase, just isn't that much work. It shouldn't take that much time. We are seeing now that with this optimization down on a higher level, we're still processing all of the clusters in the second phase. Like logically, our code is doing the same thing that it used to do. It's just structurally very different. And yes, lo and behold, like the second stage is rendering 0 objects, but it's doing this in 0.2 milliseconds roughly, instead of 4.2, right? So it is indeed not as much work. It's just that we were previously hitting efficiency barriers around the draw call dispatch. All right. So I'm happy about this. We are going to submit this code, and then we are going to clean up the mess, so to speak, so that we don't need these 2 modes and stuff like this. Let's disable sync validation again. We could keep the 2 modes, but constantly having to check both, like, it's just too much work. So I think it's going to be simpler if we just split things more neatly now, where we assume that this new mode that we've implemented is just a good idea. There's only an AMD GPU in my system. For example, we don't know an Nvidia GPU. Is this a good idea? Is this a bad idea? I have reasons to believe this can't be a bad idea. I won't go into details for why, but I suspect it's a net benefit on Nvidia as well. So there's that. All right. So let us do that. We haven't added any new files, right? Yes, cool. Today is day 20. Day 20, implement task, command submission. This mode dispatches a single draw call instead of using so the thing we were using is called multi-draw indirect, which dramatically boosts efficiency on AMD hardware for cases when we are not bottlenecked by mesh shaders, by mesh shading or rasterization work. This allows us to save a lot of time by cluster occlusion culling, which we had to keep off by default because of these issues. This change is intermediate as it still maintains both modes within task shader mesh shader pipeline. A subsequent commit will clean things up. All right, so this is super good. We're 1 hour 40 minutes into this stream, which means we should have time to clean things up now, which is great. All right. So my idea obviously worked. I wasn't 100% sure that it would. There could be reasons to believe that, two things to say. One is there could be reasons to believe that the driver / GPU could have implemented things better so that we wouldn't have to do the thing we've done. The second thing to say is there could be reasons to believe that this wouldn't have helped. Because we are dispatching, there is a question of efficiency of task shader stage in general, right? And if that is poor, then maybe it doesn't matter as much how you split things into draw calls. There was a possibility that using task shaders to begin with has a penalty of dispatch that doesn't go substantially down, or that doesn't go down to almost zero with this method of draw call dispatch. Fortunately, we didn't get there. I had reasons to believe that this would succeed based on this calculation that when you enable level of detail, there's more task shader work, but the time is still the same, so the bottleneck is unlikely to be in task shader dispatch, but you never know. The other way to be more certain about the thing that we just did before doing this would have been to use a profiler. We can't use a profiler, so mea culpa. All right, so anyway, now that the new mode is more efficient, then it is more efficient when cluster culling is enabled, and it is not less efficient cluster occlusion culling, and it is not less efficient when it's disabled. Now that this is true, we can kill the old mode. And killing the old mode is really good because it removes a bunch of code it simplifies code that we've just written, but also it more cleanly splits the pipelines. Now that we have to use two different high-level pipelines, it would more cleanly split them. We wouldn't have to do some weird stuff that we had to do before. Okay, so let's do this. So now we can just assume that this task boolean in the mesh shader pipeline is true because we are only going to use that ever. Sorry, there's one more thing we should check before making any changes. And it's not going to be a perfect check. Ideally, I don't have an actual complex scene to test on because we only work with object files for now. We don't work with GLTF files or whatever. We're going to set at some point later. There's one, how do I put this, weakness in the scheme that we have just implemented. And this weakness is that here, for visible objects, we have a loop that adds a bunch of commands. And this loop runs for a different number of iterations for different meshes because it depends on how many commands you have to add. If subsequent draw calls generate very different numbers of task groups, then you could run into some inefficiencies in the culling stage just based on this code alone. Now, I don't think it's going to be particularly catastrophic given how quickly, in general, the culling stage executes for us. But I just want to double check that on two meshes, so that's more randomness, or we can even do 3 meshes or something. I don't know, let's do Arctic Fox. On a bunch of random meshes, there's more variability in different numbers that go into the pipeline. Things are less uniform. I want to make sure that when cluster culling is disabled, cluster occlusion culling is disabled, we are not slower or not much slower than the old mode with mesh shaders. Because if we are, then it's not super nice place to be. What the heck? Arctic Fox mesh might just be very big. I don't know. I think I had some other clay models. Clay drunk. Clay panic. Okay, let's have 4 meshes. So there's like a bunch of stuff on screen. Okay. So 10.51. Okay, perfect. So when I enable task submission, times do not change. All right. Okay, so it should be safe to just remove the old mode because the new mode seems to just be better. There's no obvious case that we can check right now where the new mode would be worse. Okay. Note that within the calling code, the draw call calling code, we still need this if else because there is still 2 modes for the entire pipeline and we still support the traditional rasterization pipeline. But when we use mesh shading, we don't need the old mode of dispatch. Okay. Oh, and we can remove this extension. This extension provides us with access to GL draw ID arb. This is unsafe to use now because it is 0. So we can kill that stuff. Kill the boolean. Never use mesh draw commands. Only use mesh task commands. This needs to be in the math header. We need to do some header cleanup, but hold on, let's do this first. So do that. Do that. Do that. Do that. Do that. Do that. Now that we've done this, we can also simplify things sort of by reading the entire structure. Instead of like reading individual fields from this array every time. So that here we can just say command draw ID, and here we can say command. And in fact, some of these local variables are now like, these are 2 are kind of redundant. We can just read data from the command like later, but let's keep it like this for now. So we have cleaned this thing up. This thing had nothing to clean up. This calling shader needs to have basically the same checks. Yeah. On the high level now, we don't need task submit because it's always true, essentially. This is still true because this counter buffer is still going to be used when we use traditional pipeline, not mesh shading pipeline. Here we can just I like task pipeline name more a little bit because I mean both are kind of the same. Maybe I should keep mesh pipeline name. I don't know. Naming is hard, okay? I don't know what names to use. Oops. So this is how things work. Now, this technically we still need, but it's just different. So I guess we sort of needed this variable. This just means mesh shading supported and mesh shading enabled. In fact, I think we use this condition in a couple places, so maybe it's okay to keep the boolean, but then use this combination instead. So maybe this is what we will do. Okay. And there's some pipeline stuff that we don't need. I think this is kind of it as a first cut. Okay. Now that we are here, we can enable cluster culling by default because it works really well. And in fact, the only reason why we have a separate boolean for this is because it didn't work very well. So in theory, we can even remove the ability to toggle it independently from occlusion culling. But let's not do this yet. Things are okay. Okay, so now you enable mesh shading. It enables all sorts of culling. And now it's like really fast. And then traditional raster is now slower. Yay. The other thing that we now don't need is that when we use the traditional rasterization pipeline, we are generating mesh draw commands, which previously were dual use. They could be used by mesh shading path or traditional raster. Now this is not needed, which is cool. And mesh draw command. I wanna add. Oops. What? Okay. This is the structure that kind of like these 5 integers have to be in this order in this place because it reflects the Vulkan structure with a fixed layout. All of this just isn't necessary anymore. Oh, and then now we can also bit back some stuff here or something. Let's see. Draw call comp chill cell 138. Right. All of this should be irrelevant now. Okay. Things work. This just reduces the waste in a traditional pipeline so that we don't have to feel like random things that we don't even use ever now. So that is cool. So that's kind of the cleanup. Is this to-do comment, right? Yeah, I'm confused. This to-do comment, we already did all of this. We also pass something like this. This is not a to-do comment because there is nothing to do. We already did everything that we needed to do. Okay, so that is cool. And then this is clean. This thing is a little misleading because essentially this guy is sometimes draw command count, sometimes cast command count. So let's remove the word draw from this. So that it's just command count. Okay. What else? What else? What else? We can bitback stuff. I want to submit this as is first because I'm not sure how I'm going to bitback things. There's things to think about. What else can we clean up? I think that's kind of it. I wanted to move some function, this function, to math, different math. Just this guy, which needs to go to here. All right, I don't know. I think this is kind of it. meshlet. Okay, so this is nicer and simpler, like this removes a bunch of code. Without really like a noticeable efficiency difference. Day 20 switch to task command submission. Since new mode seems to always be as good or better than old mode, switch to it unconditionally and clean up some code. So now the cost of cluster occlusion culling seems to be small enough that even if it doesn't dramatically reduce number of triangles, which it definitely does in our case, it's probably reasonably safe to just keep it on. There are strategies that I was thinking about that we can employ to heuristically check if it's worth doing cluster occlusion culling for a given mesh based on past feedback, but it doesn't seem to be truly necessary because the actual amount of work that happens here isn't like actually super meaningful. All right, so the only other thing is that the draw command thing that we are filling, ideally we would check some limit and like not write to the buffer past this limit. But let's just leave a to-do comment there. I don't want to do this yet. We would abort essentially if command count overflows the output buffer. It's not, Vulkan doesn't have by default a defined semantics of what happens when you draw past the end of the buffer. When you use direct text semantics, which essentially just drops the write, then things that we are doing here are perfectly safe. Worst thing that happens is some objects don't fit, some meshlets don't fit, some objects don't render on screen. What can happen is that this damages, this overrides some memory someplace else, and that's not a good time. So ideally there should be a cutoff here that prevents this from happening, but for now let's just leave it to do item. Okay. So that is nice. That is cool. Right. Yeah, okay. Let's just command the previous commit. All right, so that is super cool. This is kind of what I had planned to do. It bothers me a little bit. So this total GPU time that we have, something is fishy there, because the sum total of individual stages really doesn't add up to the total. The total is hovering above 4, and the sum total should be 3-ish, or maybe even. You know what we should do? We should actually print this to console so that we don't see this crazy, like, yeah. Let's print this to console every 100 frames. Perfect. Way nicer. The timings are going to fluctuate. Some of this is inevitable. Some of this might be due to GPU clock fluctuation or whatever. Like, it's kind of has to happen, or like it's not super avoidable. But yeah, this is kind of fishy, right? So, or there's something else something weird is going on. Like you can look at this and you can say, well, if you add up these numbers mentally, we should have a frame that's around 2.5 milliseconds. But we have a frame that's 4.4. So a reminder that we don't have a functioning profiler. So we are losing time, like in some way that our timers don't detect, which is odd. We should look into that. Like, that's a problem. It could be something really boring. For example, we are not timing the final copy to the swap chain, and maybe we aren't setting things, like maybe for some crazy reason something takes like a millisecond in the frame and we just forgot about this, or maybe something else is going on. But this is weird. I think also this number is the average and these numbers are immediate. So it's also possible that some fluctuation is driving the average up significantly in a consistent manner. Let's let's test this theory. Frame GPU end minus frame GPU begin. Okay, that is actually what's happening. So our actual frame time now is 2.5 milliseconds. However, we have occasional spikes in the total GPU time. This could happen for a number of reasons. This can happen, the GPU clocks, like, there's one thing that we are still doing which is weird, sort of, which is that we are doing the CPU-GPU sync. So what happens is we have this spike of activity of now 2.5 milliseconds, which is not a lot. And then we have a lot of time, like 10 plus milliseconds, of just doing nothing. What is possible under circumstances like this is that the GPU clocks vary. Because the GPU is like, oh, I should be running at high clock because like something interesting is happening. And it's like, well, nothing is happening. Let me drop the clocks down. So maybe this is the problem. As in maybe this is why there is so much fluctuation in the time. But okay, but it looks like we aren't actually losing time in this. Like, we aren't not accounting for anything major because the total time on good frames is still 2.4, 2.5 milliseconds now. It's just that the average is throwing things off pretty substantially. Okay, so this is a problem probably for another time because it's already been 2 hours. But it's good because I wanted, if you look at the renderer that we have so far, there is parts of this that are obviously not production quality, so to speak. I think all the work that we are doing like today and all of that I think I would stand behind in the sense, not in the sense that you can take this code and copy and paste this into a production renderer, but in the sense that it's doing roughly the right things in like a way that would be close to what I would probably be doing if I was doing this as a production workload. Not always, but you know, by and large, there is nothing too crazy going on here. The biggest thing that is too crazy that we have done in the very, very beginning and just haven't changed since is that we are synchronizing CPU and GPU, and this is the thing that you would never do in a production render. So that needs to change. Changing that complicates some code, so we haven't done this. Right. So we haven't done this, but maybe we'll do this next time. I need to think about what we are going to do next time now, because so for the last couple streams, we were in this weird state where we did some amazing work, and then it doesn't like actually work to the full extent of what it should be working at. Like, Now things are working really well. There is still a problem with the efficiency of the dispatch of geometry that we are masking with culling, in the sense that I think we probably can still do better performance-wise a little bit in certain cases than we are doing right now. But the margins are getting thinner. Like 2.5 milliseconds is pretty good now, especially, so if you look, let's look at the timing on like full screen or something. This random thing, and like, anyway, things are not perfect. But yeah, so because we did cluster occlusion culling, this was really the key optimization, because until we did cluster occlusion culling, the traditional rendering pipeline could keep up with what we are doing here, because even though we did some amount of per meshlet culling, it would just reduce the number of triangles that are fed into the subsequent stage, and the reduction wouldn't be as dramatic. After we did, this is why I really wanted to fix these efficiency problems, because the cluster occlusion culling here is a critical optimization that dramatically shifts the efficiency balance between the traditional pipeline that doesn't do this and the mesh shading based pipeline that does do this. Now, you can do cluster based occlusion culling in traditional pipelines, sort of, like you can cull pieces of meshes, but it results in a substantially different architecture of the higher level render loop that is much closer to meshlet stuff. And at this point, it's merely a substitute for sort of not having mesh shaders in hardware. Like, it's not actually a nice thing to do by itself. It's just that, like, sure, you can, like I wouldn't do this if I actually had access to mesh shaders, which I do. Anyway, so all of this is to say that now we are in a spot where the actual geometry submission is like freaking good. Like, it's gonna be possible in certain cases to improve on this a little bit. We can like compress the data somewhere. We didn't beat back the thing. We should probably beat back the thing now, because it's easy. Let's beat back the thing now because it's easy, so that we don't have this as like a leftover thing to do. Now, I was talking about the fact that this bit thing might just be redundant. There is a way to do things differently that doesn't require storing these bits. It's a good idea. I think we might do this. I don't know when. I think we might do this. I kind of should write a to-do comment about this. I'm not sure where. Let's add this. Oh yeah. These to-do comments are not correct anymore, but there's a way to implement cluster visibility persistence without using bitwise storage at all, which may be beneficial on the balance. So we should try that. If we can do this, then it will simplify things a little bit in some places and complicate things a little bit in different places, and who knows if the balance is worth it, but it's something worth trying. So there's like stuff we could do around geometry submission, right? However, by and large, and like, I don't know, our LOD selection scheme right now is just not good at all. It's just whatever we wrote on stream in 5 seconds. So there's, generally speaking, stuff to work on, but there's few super fundamental things to work on. So like the thing we did today was really fundamental. The thing we did on the last couple streams were really fundamental, except I think for the previous stream where we just tried to make things faster and mostly failed because of this bottleneck. But not much else is left from the geometry perspective. So there is options. We can start venturing into the textures and materials category, which I really didn't want to do because there's a lot of extrinsic complexity. There's like a bunch of boring stuff that you have to do to actually get to the problems that are interesting. But maybe we'll do that, or maybe we'll just do a couple streams around sort of cleaning up the fundamentals, and sort of maybe the series goes back on hiatus. I don't know. My sabbatical also ends in the month, and I'm going to be traveling for 2 weeks of that, so I'll just have less time to do this. So I don't know what's going to happen in the future. But let's bitpack the task command so that we leave it off in a great place, and I'll answer where, if there are questions on chat that are remaining, I will answer them, and then we will end this. But this was really, really, really productive. Like, we improved performance by a lot by unblocking the optimizations that we've done previously so that they can reach their full potential, which is great. Oh, one thing I'm curious about actually, while we're here, let's check how many draw commands we even have. Okay. Now we should be able. Oh. If I print this every frame, is it stable frame to frame? It's not very stable frame to frame because the draw color occlusion culling doesn't work. Oh, okay. Fine. We are going to. Right? All right, I don't want to think about this, whatever. So 23,000, so this is actually not too bad. So we are, I forget, whatever it was, times, I think we're using, what is it, 20 bytes without bitpacking. So this is like under half a meg. This is really not that bad. I was trying to figure out, do we care, how much do we care about bitpacking of the command data, and it looks like we don't care a whole lot. We might care more for larger scenes, although the nice thing about this one is that it's only emitted for visible objects, let's put it this way. Might be invisible clusters, but visible objects. So it's not that bad in a sense. Anyway, so okay. So this must be 0.63, so this is 6-bit. This is 1-bit. So this is, let's say, 24-bit. This is, let's say, 24-bit. So realistically, the thing we can bitpack is just this 1 bit, put it someplace, I don't know where. We can just redo the thing that we did initially when we started the stream, which is pack these two guys together. And maybe that's a good idea. Let me look at, again, it's just that if we drop this offset completely, then we will have to change the bit packing, which is fine. Okay, and then this guy is only used to compute this guy, and this guy is used here. Okay. Yeah, I don't know. So like if we remove this, let's say this doesn't exist. It's not like a very obvious place. Yeah. Let's just leave it as is for now. It looks like the total amount of memory this occupies is actually pretty trivial. We're using like a fraction of a buffer that we've allocated for this stuff. And if we rework how this works, then the bit packing decisions would be different from what is the best logical thing to do right now. So let's just ignore this. GLSL, like in C++, if this were C++, I would just be like, whatever, let's use bit fields and call it a day. GLSL doesn't support bit fields, I don't think. And so all of this changes the code in ways that are just like, it's too much work to do and undo all the time. So well, let's just not do this for now. But this might disappear in the future. In fact, there was a to-do comment that we just fixed. If we do that, we can drop meshlet visibility offset et al. From basically everywhere. All right, let's end there then, because we are in a really good spot. Like I need to think about structurally what we should do in the future. Everything tactical, I think that we should have done, we've just done. The only tactical steps that remain are ones that are not like obviously a good idea. Yeah, it's not a fence, it's just a wait for idle. It's equivalent to waiting on a fence. There is a command vk device wait idle, which you should basically never use in a production renderer ever. There are cases, I think we probably should spend the next stream removing this, not just because it's the glaring obvious thing you should never do in a production renderer, but also because not doing that requires a bunch of other stuff in other places that's good to understand, right? So I think the fact that we did this is a great shortcut for when we were starting to develop things, but it's not like it's about time that we've removed it. But yeah, every frame after we submit the frame to the GPU, we immediately wait for all GPU activity to stop. Using this, we could have waited on a fence when we submit a frame somewhere. I guess we don't use fences right now, but like you can add a fence. Yeah, we don't use fences right now. You can use a fence. So you could submit a fence and then wait for it immediately. That's the same thing, which is also a thing you shouldn't do. And there is also some old code that uses Nvidia extension for, let's actually remove this. There is some old code that uses Nvidia extensions to do sort of, to figure out where the code is crashing. It's not bad code necessarily, but it's kind of polluting a little bit. Sort of. Like it's NVIDIA specific, I don't even have an NVIDIA GPU anymore. Let's just remove this. While we are here. We never use this guy, right? Yeah, we use this to debug some stuff. Let's remove this as well. Let's leave full barrier. Full barrier is a good convenience function. And then there are like AMD extensions, I think, for this as well, but let's just, like, it's gonna be easier to deal with this code if it had few if it had fewer sort of things that we could toggle. The other thing that we should do at some point is to rework the way we do descriptors. I said that at some point we might do this on Mastodon, I think. So maybe we'll do that at some point. Was this it? This was less than I remember. Checkpoint count, checkpoint data. All right, yeah, okay. Yeah, I think this is it. Okay, so this was useful at some point to diagnose, but it wasn't even like, it's sort of diagnosing GPU crashes, but I think the GPU crash that we were diagnosing was due to a driver bug. And like, again, this is Nvidia specific, so it's not actually very useful for us now. So might as well remove it for now. Yeah, anyway. Yeah, so swap chain recreation is the thing I was, when I said you should never use it in production render, I was like, there is a better way to do swap chain stuff that doesn't use device weight idle. I'm actually not an expert on this topic yet because there is a new extension on this subject that I haven't looked into, which is swap chain maintenance or something, which using that should help you like resize swap chains essentially without having to wait for idle, and that's nicer. I forget if it's already supported on my driver. It's an extra extension that is optional. In fact, I think it might be, I forget if it's KShar or AXT. So basically, essentially, when we remove device wait for idle, I think we might still use it when you recreate swap chains. And then there might be at some point in the future, maybe it's a good idea to do completely sort of weightless submission loop, which you should be able to do with a new extension. But yeah, in a production renderer, you probably use wait for idle in two places. One is before you tear down everything, just for simplicity, like to wait for pending frame, right? You can do this with the fences or semaphores, but some renderers I've seen just do wait for idle, which is fine. It happens once in the program lifecycle, right? And then the other one is whenever the swap chain is recreated, just because the alternative is tricky. Given all the layers of culling, is it worth implementing a G-buffer on top of the renderer at this, or is there a different approach? This is all orthogonal to what we were doing, more or less. So like there is a question, we were rendering things with a very simple shader. We are doing occlusion culling really well, which means that you will have a little overdraw, relatively speaking. However, you still may decide that like when you're choosing between deferred rendering versus with a gbuffer layout versus something like forward plus where you don't do a gbuffer at all, versus something like forward plus with a z prepass, versus something like a visibility buffer where you only render geometry once but it's not a full gbuffer laydown, there's a lot of things to consider when you're selecting a technique like this, right? Certainly one of them is the efficiency of your geometry submission and the degree to which you can save time by culling things that are invisible. For example, once you're doing per cluster occlusion culling, the efficiency of the depth prepass by itself drops, because Z prepass is really helpful to reduce the overshade of pixels with overdraw. Occlusion culling does a similar thing at a higher level, as in it removes more work from the pipeline. But it is not as efficient as in if you do a Z prepass, you're guaranteed that in the second pass you're not doing any redundant shading on pixels. With occlusion culling, there's no guarantee like this, right? Again, we've talked about this before on the last few streams. There's the efficiency component of any culling that you do. So it's hard to know. The other reason why it's hard to know is there's a few other things like that are worth pointing out. One is we are using artificial scenes to test the efficiency of a lot of stuff, right? On the real world scene, things may be different. The other one is some forms of culling are more difficult or more annoying to do with skinned objects. Maybe you have a lot of skinned objects because maybe you have like tens of thousands of characters, and that's what your graphic scene is about. Like, it's hard to make a general statement, right? But it is true that, let me put it like this. It is true that the culling that we are doing is slightly changing the balance of decisions around high-level sort of technique selection. However, I think the major reason why you choose a high-level technique is slightly different from what we've been doing. For example, you go deferred in general to try to change the equation between sort of lights and shadows and objects and materials in terms of complexity. And what we are doing right now doesn't affect this. You may want to go defer shading instead of forward shading, for example, for efficiency reasons, but not because it somehow allows you to shade less, which it sort of might, but sort of not really. But really what defer shading can give you, for example, is more efficient utilization of fragment shader units because of the reduction of quad overshade. There's this problem where you might be doing 4x more, sometimes even more than 4x more pixel shader work than strictly speaking is necessary because of how the GPUs work. And defer shading helps alleviate this a whole lot. But it's not, this problem doesn't happen because you have an overdraw. This problem happens even if you have zero overdraw. So it's hard to know. You really have to test. You really have to test. It's hard to make a general statement like this. Yeah, so the maintenance extension is super recent. I don't VK, KHR, swap chain. That is clearly not that. I think it might be VKX. Yeah, VKX swap chain maintenance one. So it's actually talking about some swap chain education stuff. There is present mode change, which I think is less interesting. There is releasing acquired images, which is a little bit more interesting. So anyway, like this makes some aspects of working with swap chains nicer from the synchronization perspective of what to do when things change. But it's X. So one fortunate thing that we had, one fortunate property of a lot of work that we've done was that we used more extensions, I think, when we started the render or at various points during the render, but then a bunch of them got promoted to a core version of Vulkan, and so we didn't have to use extensions. In fact, if you look at the total number of extensions that we use like a bunch of fairly advanced stuff, but and there's a lot of features that we request, but most of them are core features. We only use 3 extensions at most. This one we should just stop using probably. I like it, and in fact it's supported on RAD, but AMD is adamant about not supporting this on their main driver, and like it's never gonna make it into a core Vulkan version, and it's the one that I'm sad about, but whatever. And then we use the swap chain because we must, and then we use the mesh shader because, you know, we really want to. That's it, right? So we just removed one extension from this list, which was the checkpoint for Nvidia. So from this perspective, like it's not like using extensions is particularly difficult. It's just that it increases the number of paths that you have to test on various GPUs and stuff like that. If you don't have to do this, that would be nice. And the problem here is that ext is usually assigned when you see an extension that is vendor specific, like Nvidia or AMD. Then it's like, okay, this vendor will support it, other vendors probably won't, even though exceptions happen. When you see a KHR extension, it's a sign that A, all vendors are probably going to support it, B, that a future version of Vulkan is probably going to have it out of the box without using an extension mechanism. ext is usually a sign that more than one vendor said, oh, hey, we kind of like this idea, we will implement this, which is why it's not vendor specific. But it is not core enough, which might be because some people said they don't like the extension or whatever. And it is unlikely, less likely, I should say, that it's going to be promoted to a core. Especially here it's weird because it's like even the main swap chain thing is not part of core, because you can ship a conformant Vulkan implementation that doesn't know how to render to swap chains, like in a sort of data center context, right? Headless rendering. And this is extending a KHR extension. So maybe I shouldn't read too much into this. Maybe at some point Vulkan will say, if you support this extension, you must support this one. And they change the definitions of some stuff here somehow. But for now, this extension essentially means you have to implement both paths, because there's no guarantee that this one is going to be supported long term. Anyway, yeah, so descriptor buffer is the thing that we don't actually need right now, because we have so few descriptors. Descriptor buffer is an extension that is probably going to make things easier if we are going to do materials and stuff like that, which I don't know yet if I want to. It would be nice, I should say it would be nice, now that things are really, really solid from like every perspective I can think of. It would be nice to go from this picture, which is a lot of synthetic meshes, to like, oh, we can just render like Amazon Bistro or whatever, and things work really well. And we can do this today without textures, materials, but it would be pretty weird. It would look pretty odd. So from some part of me wants to do this, and then some part of me dreads the work, because there's a lot of not just work, but like boring work. You need to load GLTF data. You need to open textures. There's a lot of textures in a scene like this, so you need to compress them to a hardware-specific format. How are you going to do that? What command line tool do you use for this? Then you need to load all of these images into memory. So you need to like write an allocator and stuff like this. And all of this is not exciting for me, because I've done this, like you do this in every API, except for writing an allocator. But even if you don't need an allocator, there's a bunch of C++ code around management of these objects. So it's not exciting work by any stretch of the imagination. There's a lot of busy work, right? And a lot of this work that we have done here so far has been minimize the amount of busy work, except for cases where busy work is necessary to get things going in general, right? But we've tried to keep things very compact. And some things that we needed to do that like to sort of to make things going are somewhere between busy work and interesting work. Like we had to parse PRV bytecode because I decided I don't want to hard code some things into C++ code. And this is sort of busy work because there is nothing fundamentally exciting about parsing PRV bytecode. It's just a bunch of bytes that you just go through and like figure things out. But I've never done this before, and so this was cool for me. All of this image texture work is like, I haven't written a production bindless renderer or even a toy bindless renderer, but getting to the stage where you need to do this requires so much preparation that I don't want to commit to any of this yet. But maybe at some point. And like just right now, adding ext descriptor buffer is possible, but not very productive because there's not a whole lot will change. Maybe it would make sense. The one thing I say is we are using this push descriptor extension right now, if available, which simplifies some stuff for us. But we had to implement a fallback to work on drivers that don't do that. Maybe it would make sense to replace that extension with the ext descriptor buffer, because push descriptors are pretty obviously not on the way out, but like I don't know how to say this without offending people, so I will not say anything. But ext descriptor buffer is more of a forward-looking extension. Like the fact that it's an ext, I think, is just a sign that not everybody wants to commit to it, but I think all desktop vendors committed to it from my understanding. So maybe that's a thing we can do. I don't know. Anyway, we will see. So that's kind of where we will end the stream. Things went really well. I will push things. I have pushed things so that if you have a different GPU, you can pull the code, build the code, run the code, and hopefully the code works and is fast and faster than it used to be. We still support toggling between cluster occlusion culling on and off separately from object occlusion culling. Maybe we'll remove that in the future. But for now, you can still assess the benefit/drawbacks that specifically gives you on your GPU in question. Oh, and the one thing I forgot to mention is there is still definitely, we need to do a stream where we look at Arc, Intel Arc, but that requires me actually setting it up and stuff like this. So maybe I'll do this next week, and so maybe there's going to be a stream next week about Arc. Or maybe some things will go wrong with software setup, we'll see. With that, thank you everyone for attending the stream, and I'll see you next time, whenever that is and whatever the subject of the stream is going to be.